Hey guys, welcome back. Day 15 here, and we're talking about periodic trends. And these trends are something that happens due to how the electrons are arranged in atoms and how the atoms are arranged in the periodic table. All right, just like humans have trends. Now humans decide if we take the trend or not. Like if there's seasonal trends or fashion trends, those are decisions. Atoms don't make decisions, but just like human trends, not every atom perfectly follows the trend. All right. So if we look at the periodic table that we just covered previously, we remember like group 1 all ends in S1, group 2 all ends in S2. You got D1 all the way to D10. You got P1, P2, etc. And so that the electrons are arranged very systematically, especially like period 1, period 2, period 3, right? And so there are some very systematic ways and very systematic properties that happen because of this arrangement. Now, of course, as you guys know, the D block and the F block, a lot of exceptions in their electron configuration, and so there's some exceptions in their trends, and sometimes the trend doesn't exactly work well, and that's okay, but there's still a general trend, and we want to talk about those general trends. And so what are those general trends? Atom size is a trend. The size of the atom, the size of the ions, right? Ionization energy. Right, is a trend that systematically varies throughout the table. Electron affinity. All right. Electronegativity. Metallic character. And density. All right. So those are our trends we're going to talk about. And I don't remember. We will talk electronegativity, not in this one. That's coming up when we talk about bonding. All right. But right now, everything else we're going to talk about. So let's dive into radius, the size of the atom. And we can measure these using different various forms of electromagnetic radiation from X-rays or other light rays. And we can figure out their metallic or covalent radius. So the metallic radiance is half the distance between two nuclei in the metal, right? So you take a piece of gold, X-ray, get two nuclei, half the distance between them, that's the metallic radius. The covalent radius is like take a small piece of ice, shoot, right? Well, actually, we wouldn't use ice. We'd use, let's say, diamond. Take a small piece of diamond, X-ray, boom. You get half the distance between two carbon atoms. That's the atom size. All right? And so now the trend, right, typically as we go down, right, as you go down here, right, we increase in size as you go down the table. And that kind of makes sense, right? Again, if you're looking at a table, which is always a good idea in these videos, have a table ready, right? Hydrogen is going to be smaller than lithium, and that makes sense. Lithium is going to be smaller than sodium, and potassium is going to be smaller than rubidium, right? Francium would be bigger, right? As you go down group 1, the bottom of group 1 should be bigger than the top of group 1, because obviously hydrogen weighs 1 gram per mole and francium weighs around 223 grams per mole. That's a big difference. So you'd expect francium to be much bigger. What's weird is that we decrease, and that's a hard decrease, in size due to increasing nuclear charge. All right. Well, so, okay. what's going on here? Why would hydrogen be bigger than helium? Why would lithium be bigger than neon? And it's not even close. Like, they're almost double the size. Lithium's almost double the size of neon. Sodium's like double the size of argon. I mean, close to it, okay? And so what's going on here? All right. Okay. Well, this leads us to effective, I'm going to skip a little bit here, effective nuclear charge, right? And that's the actual positive charge, right, that is experienced by an electron in an atom. What do I mean? So if we look at helium versus lithium here, I got helium and lithium. So I'm going to try to nicely zoom in. All right. Helium, I have how many protons? 2. So this would be 2 plus there. Lithium is 3 plus. Okay. And then we got our electrons going around. Helium has an electron, right, in 1s, group 1, okay? Now, we can look at this really well in helium. If I were going to remove the first one electron, doesn't matter which one, the first electron to remove, right, that first electron, right, to remove, that cost me 3.94 times 10 to negative 18 joules. All right. The second electron to remove is 8.72 times 10 to negative 18 joules. Right? Well, that's more. That's bigger. So this is less and more. Right? And the reason is this is not screened. The second electron is not screened. Okay? And the point of that is electrons are shielded or screened by other electrons. All right? So even in helium, when they're in the same orbit, so to speak, or the orbital, they're screened. So if we go to lithium here, lithium, we have electron, and then we have an outer electron, right? So we have the 1s electrons and we have a 2s electrons. Well, these electrons in 1s, right, they're going around and around and around and around, right? And so there's a shielding or a screening that this electron in 2s is feeling. All right? Okay? And there's a formula for this. I'm not going to ask you this. But there's a formula, right, for the effective nuclear charge, and it's Z for the nuclear charge, effective. So the electron, for the valence electron, it feels a charge of 1.28. So instead of being plus 3 protons, it's actually 1.28. Okay, so what does that do? That causes this to actually increase what it should be, right? So the distance between the 2s and the 1s is actually further than it should be, okay? Because the electrons are screened or shielded from each other. So, all right? But as we get more and more electrons, if we scoot over, right? As the proton, whatever the positive charge is, you have 2 electrons here, right? Going around. But as we get more and more electrons, right? The electrons in the second orbital, right? The second energy level, there's more charge there. And Coulomb's law, there's more charge, that means there's more force of attraction. And so what happens is as we go across, right? As we go across, we actually feel more and more of the nuclear, like the atoms contract. Right? It's kind of neat. All right? And so as you go across the periodic table, you have more and more force holding them together, so they get smaller and smaller and smaller. Until then, we get to the next level, and then it gets big again, until all those 8 electrons happen. And then they get smaller and smaller and smaller as we keep going across the periodic table until you get to the next level, and then it gets big again. All right? So that's how this kind of works. Okay? All right? Now, what we have up here is talking about gallium is small than aluminum due to the 3d orbitals. All right. Okay. So 10 electrons on the element without increasing the shielding. All right. So like this happens. These are some contractions, and there's like the lanthanide contractions, and that's then for just so that you know that, like, again, the trend is, there's some variances to the trends. All right. Like, I'm not going to test you. What's the lanthanide contraction? That's not a Chem 1 like major concern. Okay. All right, but it's real, and I want to explain that to you, right? Okay, because the valence S&P electrons and orbitals determine the size and are pulled in. Okay, and so because of some happens in the D's and the F's, there's some changes. All right, I want you to note that. So if you ever looked at like a chart of atomic radii, and you notice like, whoa, hey, look, there's some weird things here. This explains some of the weird things. All right, so that's kind of what's going on. We have the electrons are in the S&P get contracted as we go to the right. And so as we go to the right, we get smaller. As we go down, we get bigger. Now, I'm not going to ask you the difference between, let's say, iodine and selenium, or sulfur and arsenic. That's not the big ones. I just want you to know the overall trend, okay? Overall trend. Next up is ionic radiance. When we remove an electron, right? So if we think about electron, we know that the protons and neutrons are in the nucleus, right? And that's the mass of the atom. And then we have the electron outside the nucleus, and think of the electrons as the volume, right? So if we remove the electron, right, we're going to decrease in size, right? Because we are removing volume, right? So it's a huge volume removing, okay? All right, so think about it. Lithium moves an electron, and it's less than half the size, okay? If you add electrons, it's the opposite. You increase in size. I don't like that C. Right? Because we are adding volume. All right? And the more electrons I remove, the smaller I get. And the more electrons I add, the bigger I get. So a 2 minus electron, or atom, sorry, 2 minus atom is bigger than a 1 minus atom, in the same period. Okay? So that's the size. So cations, the takeaway are cations, small, anions, large. That's the takeaway, right? Now it's the same thing. So if you look at group 1, lithium plus is going to be smaller than sodium plus. That makes sense. Just like fluorine minus is still going to be smaller than chlorine minus, right? So fluoride is smaller than chloride. Okay? But oxide, O2 minus, is actually bigger than fluoride, F minus. All right. Next up, big one, ionization energy. Right? And this is the energy required to remove an electron from an isolated atom or ion in the gas phase. It always takes energy to remove an electron. Even if the atom wants to get rid of it. So for example, aluminum, right? Aluminum metal, 13 protons, 13 electrons. Goes to aluminum plus, 13 protons, 12 electrons, right? This would be the first IE. All right? And then you go to aluminum 2 plus. All right? And so that's 13 protons and 11 electrons. And that would be the second ionization energy. Sometimes we write it as you see IE1, IE2, IE3. And then there is the third. 13 protons and 10 electrons. And that's a big one. 10 electrons, that's neon, right? That's isoelectronic with neon. And so that's because, all right, aluminum likes to be plus 3 because we're isoelectronic with neon. It's 1s2, 2s2, 2p6. We're happy. Good electron configuration. That's the third. You know, there's also a fourth. Can you go to aluminum 4 plus? Yes, you sure could. You still have 13 protons. Now you have 9 electrons. Not as stable, all right? Okay, right? Because if you look at this, and for this case, right, and again down here, we show you that IE1 is always smaller than IE2 and then IE3, right? So IE1 here is going to be less than IE2, right? Which is going to be less than IE3, which is going to be much, much, much less than IE4. Why? Because these are valence electrons, and this would be a core electron. So there's always a much bigger energy requirement to get rid of a core. You can strip all the electrons away from the atom. That's doable, right? You know, photoelectron spectroscopy does this. Not unheard of, okay? But if you're going to the chemistry lab, right, you're going to do a reaction with aluminum, making aluminum plus 3 is pretty easy. Making aluminum plus 4 extremely hard, all right? Not that it can't be done, but it's going to be extremely hard. Okay, so what's the trend here? What is the trend with this? All right. And so as we go from left to right, so hydrogen to helium, lithium to neon, right? We increases as we go from metals to non-metals across a period. So it always increases. Right now, a little caveat to this: the noble gases, right? They don't really want to participate in ionization energy or the next one, which is electron affinity, and that's okay. All right. They don't really want to participate, and that's just what it is. All right. They're hard. They're very stable. Now, one thing that this is the trend for the first ionization energy. Sometimes the trend for the second is a little bit different, okay? So, this is the first. Now, it decreases as you go down the table, all right? So, i.e., it decreases as you go down the table or group. That means hydrogen has a higher ionization energy than lithium. Lithium has a higher ionization energy than, say, potassium. Right? Francium would have the lowest ionization energy. Okay? And think about it. Francium, 87 electrons. Lithium, 3 electrons. Lithium's going to have a huge, even though lithium wants to give away that electron, it's going to have a huge feeling of losing 1/3 of the electrons, where francium loses 1/87th of the electrons. Okay? That's why. Now, one thing I want to say, a little note here. All right. Half full and full orbitals are more stable. So if you're looking at ionization energy, you're going to see it go up, 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 right? But then nitrogen has like a higher ionization energy than oxygen. and it goes back down, right? So when you have, you know, 2s is one, all right. So 2s2, 3s2, right? They're a little bit more stable than predicted. You got 2p3, 2p6, 3p3, 3p6. They're more stable. So half full and full orbitals are more stable. All right. So if you ever see a trend, that's what we're talking about. Electron affinity. All right. Electron affinity. This is the energy change associated with the gaining of an electron. Think energy released. Energy released. All right. And so your example here, chloride, or sorry, that's backward. This shouldn't be this way. It should be the other way. It should be going this way. I know it's backwards. Electron plus chlorine going to chloride. The energy required depends upon how much chlorine wants to keep the electron. All right. So yeah, it should be written electron plus Cl going to Cl minus. And it depends on how much chlorine wants to be chloride. Now, typically, we increase the electron EA, electron affinity, increases as we go from metals to nonmetals. Right, across the period. Okay. And it typically decreases as you go down a group. Now, example, oxygen. So O gas plus an electron going to O minus gas. EA1 is positive 141 kilojoules per mole. That looks like oxygen does not want to get an electron. However, once O has an electron, the second EA, right, EA2 is negative 744. So oxygen, right? So if you look at both steps, it's very exothermic, very negative energy, which energy is released when oxygen gains 2 electrons. All right? And so sometimes, like, you look at the trends, like, oh, well, I know nitrogen likes to be negative or oxygen likes to be negative, but the first EA is actually positive. What's going on? Well, it's more than one process. It's the overall process we're talking about. All right, so that's electron affinity, energy change associated with gaining an electron. Metallic character. Now this one, right, basically metallic character, how easy it is to be oxidized. They tend to be shiny. We like shiny, right? Right, they're good conductors, heat electricity. You can bend them, put them into wires. All right, and so what happens is metallic character decreases as we go from metals to nonmetals. Across the period. And increases as we go down the table or group. All right. And so it's kind of the same it's the same as ionization energy, right? And so if I look at francium, well, let's make that a really lowercase r, and helium, right? Helium would be the least metallic, and it'd have the highest ionization energy. Francium would be the most metallic and have the lowest ionization energy. All right? Hopefully that makes sense. So, let's repeat that. Least metallic, most metallic. Highest ionization energy, lowest ionization energy. So that's kind of the trend this way. Right? The trend kind of goes that way. But it's not perfect. It's not like a perfect straight line. It's more of a, all right, it's a trend. It's an overall trend, not a perfect straight line. All right, the last trend we're going to talk about is density. All right, density increases as you go down a group. Because if you think about it, you look at any of the groups, boron, aluminum, gallium, indium, or if you look at any, like that's just pick that one. So group 13, right? You're gaining size a little bit, but you're gaining a lot more mass. So your mass is going up more than your volume is as you go down. Now this is just per group, right? Just a group. It's not the whole table. Now, I need to do this. Nope. Where am I at here? There we go. The next thing we need to talk about real quick is the electron configuration of ions. Okay. Right? And we know that the main group, so what's that? That's 1, 2, 13 to 18, right? Tend to be isoelectronic with the noble gases. All right? So anions, pretty straightforward. All right, we keep adding electrons until, right, my number of electrons is reached. Example, O2 minus, right? So oxygen is 1s2, 2s2, 2p4. Well, I get it, add 2 extra electrons, right? Okay, so I just add 2 more electrons. So O2 minus is 1s2, 2s2, 2p6. And that looks just like neon, right? That looks just like neon. Isoelectronic with neon, which is what we expect. All right. So in an anion, you just keep adding the number of electrons you need to add. That's easy. All right. The cations become more complicated. All right. Cations, we remove electrons. They don't always come off the same way. Some of them are pretty straightforward, right? So for example, aluminum. Al versus Al3 plus. Aluminum. So aluminum, I would have neon. And then we have 3s2, 3p1. Well, I'm going to remove 3 electrons. Well, what electrons I'm going to remove? 1, 2, 3. Right? And so we're going to still have neon. But we're going to have 3s0, 3p1. So technically it's just isoelectronic with neon. And that makes sense. Right? So do I have to write the 3s0, 3p1? I'm going to write it for you guys. And right now I would recommend, I put a 1 there. Holy cow. I'm so sorry. That should be a 0. Let's recap. Aluminum should be neon 3s0, 3p0. I am sorry. And aluminum should be isoelectronic with neon. Now, do we need to write this? No, it's not like just neon was sufficient. However, I would encourage you to do so because it's good notes, right? Now, let's talk about a different one. Let's talk PB, PB2 plus, PB4 plus. All right. So if I look at lead, and lead should be xenon, 6s2, 4f14, 5d10, 6p2. Now, some books will rearrange this to you guys, right? And they'll put it in what we call stripping order. And so they'd put the 4f14 because that's the lowest n, then 5d10, then 6s2, and then 6p2. Because the p electrons come off first, then the s, then they would go to the d, then they would go to f, right? So if we were taking electrons, that's how they would go. So PB2 plus would still be xenon, and 4f14, 5d10, 6s2, but there's no 6p. All right. Now, if you write it 6s2, 4f14, 5d10, 6p0, or not even the 6p, I'm happy. If you write it 6s2, 5d10, 4f14, I'm happy. Okay? I'll be able to read that. So if you ever write that down, I can cover that, all right? I'm not that picky on it. All right? If you go to 4 plus, we're going to lose the 6 S's. So in 4 plus, we're going to have xenon, 4f14, 5d10, and then you'd have 6s0, 6p0. All right. And again, how you write it, I'm not too worried. Okay. Hopefully that makes sense. Now, let's do another example, though, because I want to do it when we lose D's. And so if we look at gold. No, so let's look at gold. Gold. AU plus, AU3 plus. All right, so gold is special to begin with, all right? Gold is xenon, right? And we have 6s2. No, we have 6s1, 5d10, right? And 4f14. Again, so stripping order, xenon, 4f14, 5d10, 6s1. So gold plus would just be xenon, right? 4f14, 5d10, and then we have 6p0, or 6s0, 6s0. Gold 3, what do we do? Well, gold 3, xenon, 4f14, 5d how many? Well, 5d8. 5d8, and it's 6s0. All right, if you want to write it. So those are examples of losing electrons, right, and how they're configured as you lose. So gaining, losing, right? Hopefully that works. If you have any questions, feel free to reach out, and we'll see you next time. Goodbye.